So, okay. So the first speaker of this session is working from Amazon, Ségolène, Dessertine-Panhard.
Perfect. 1 second. Thank you. Does it work? Yes? Perfect. So first of all, I would like to thank the organizing committee to have us today. Even if I'm not part anymore of the pure academic quant world, it was super important for me to be here today, and because Peter was much more than a mentor for me. Thanks to him, I jumped into a data science career in the tech world when I left NYU 5 years ago. But I will never forget the Garch model, as they helped me to understand the deep learning model I used and work on now at Amazon. Over the last year, we stayed in closely touch with Peter, and he was always very supportive and passionate by new ideas and models. He used to care a lot about people, and he will remain a model for me. So thanks again, Peter. Merci beaucoup for everything, because you are deeply missed, and I will keep you in mind. So the goal of this talk today is to provide a general overview of Amazon forecasting philosophy and provide insights regarding our cloud computing experience, because it is something Peter was super interested in. So it is indeed a fascinating world, and I'm very lucky to work with great colleagues such as Yash. So we're gonna start today with a definition of why forecasting in the cloud is important. After, we will provide you a quick overview of the history of forecasting at Amazon, of what kind of model we used. And after, Yash will provide you some insights derived from our experience as a cloud practitioner. So I am Sego, and I have been at the Amazon for 4 years now, and I was faculty at NYU FRE between 2015 and 2017, so 5 years ago.
I think I have this. Hey everyone, thank you for inviting us. And my name is Yash. I've been with Amazon for almost 4.5 years now, and thank you, Ségolène, for giving me an opportunity to collaborate with you on this talk. I was talking to Ségolène earlier about this today, that it's great to see having so many technical experts in the room together, and looking forward to impart a little bit of what we've been doing and share that with you. So,
thank you, Yash. So, both of us are scientists at the Amazon Machine Learning Solution Lab, and our mission, and this is for our current, our daily job, is to help AWS customers. So AWS is the cloud of Amazon, is to identify and implement customer highest value ML use case to accelerate adoption. So I am specialized in supply chain optimization and forecasting methods. So, as a practitioner in the cloud, I think that cloud computing provides a lot of value. I remember when I was doing some R code on my laptop 15 years ago when I was doing my PhD, it took me a while to do like some analysis of some portfolio and so on. And now, thanks to the cloud, and I think this is something Peter was interested in, and this is the reason why he starts putting these some classes at FRE, is that cloud provides a lot of value to practitioners, especially. And because, for instance, and you know that as well, that data, and especially in finance, can come from various sources and sometimes need consolidation into a single system. And I think this is one of the most important values that the cloud brings, that you can work into a single environment. After, another thing which is super important, and this is when you need to do some, for instance, imputation on missing value, etc. The cloud helps you to parallelize your workload, and because you can use some GPU and CPU on demand. After, this is something we do as well with Yash, is we create some automatic ML pipeline, and we can automate the ML workload we create. And after, thanks to the cloud, it is easy to iterate, to evaluate, to try different models in parallel, and we are able to improve accuracy. So forecasting at Amazon is, of course, something not new, because we deal with millions of time series, and we saw a kind of evolution over the last year because of the availability of big or large enough data sets and computational availability. So we start using, and this is something we saw that we went from local statistical model to more global models right now. And so we start using machine learning model in 2007 when we introduced the sparse quantile random forest model. And since maybe 2015 now, we heavily used machine and deep learning model, and we were able to see an improvement in accuracy of most of the model we run on the cloud. So we won't go into detail a lot in math, because I think we have already seen a lot of math over the last 3 days, but I think what it is important to have in mind is that at Amazon and at the ML Solution Lab as well, we work on probabilistic modeling. So we don't forecast point in time, but we are more in a kind of a probabilistic approach, and especially when we use a large collection of time series. We've got two main modeling approach at Amazon: a generative and a discriminative approach, depending on how the target Z is modeled. So here. So we will go into detail about the difference between generative and discriminative, but the idea is that discriminative models are much more flexible than generative, and this is because we use, again, much more time series than before. So in a nutshell, a generative model assumes that the given time series are generated from an unknown stochastic process given the covariate X. The process is typically assumed to have some parametric structure with unknown parameter phi, and the unknown parameters of the stochastic process are typically estimated by maximizing the likelihood, which is the probability of the observed time series under the model, the model P, given the covariance. Some of the generative model we heavily use are, of course, the classical model like ARIMA, ETS, and so on. Some Gaussian processes, state space model, and this deep state space model and deep factor model. So this is here already the generative approach, which is quite, I would say, we need to do some strong assumption, and sometimes they are less flexible than the discriminative model, and which is much more what we call now deep learning, because you have these models are much more flexible given the fact that the conditional distribution are computed through neural network. So we distinguish between autoregressive model and sec-to-sec, sequence-to-sequence model, when we use some discriminative model. Again, it is like really what I used to teach at NYU. It was like all these statistical models, and especially the ARIMA and so on. And we see that when we deal, even when I was using, like, for instance, some VAR or VOCM model, when you had at least more than 10 time series or this kind of stuff, the model was not relevant anymore. And this is the reason why now we use, like, for instance, some non-parametric time series forecaster or DPR model, which is a kind of augmentation of the autoregressive model. But we use now some RNN time series and LSTM or LSTM model. We've got as well the VoidNet neural network, which is dilated causal convolution at its core. And we've got as well the sec-to-sec model, like heavy use of transformer model on time series. So I put here, like, the kind of different model we use at the ML Solution Lab and, more generally speaking, at Amazon. And Yash will explain you how it is, how do we take the good one and how we iterate on these different models. So you can see that we've got some local model, but now we rely more and more on global model and with different flavor. All these models are available on the GitHub of the AWS labs. Thank you.
Yeah. Thanks, Ségolène. So yeah, as Ségolène just mentioned, we've got different kinds, this whole suite of different models that you could technically use when it comes to time series forecasting. But then how do you select one, right? I mean, is it a one size fits all? And one of the common things that we often see in the industry is when stakeholders come in, and not every stakeholder is always familiar with the depth that is required when it comes to time series forecasting. And they often come up with the idea that, okay, you know what, there's this one model that we want to try and it should work for everything. And it doesn't necessarily always translate that way. We often talk at Amazon as something called as a hub and spoke approach. You have a central model or a common model that tries to maximize across many different time series products, in this case, financial data sets as well. And despite there being a common central model, it's not really likely that it will actually fit all the use cases. So in that case, what we actually do is we come up with spoke models, which are niche use cases that have been identified by the business as being equally or sometimes less important or sometimes more important use cases, right? So an example would be if you've got seasonal products or seasonal time series, things where you probably do purchase decisions maybe every peak season for holiday seasons or anything like that. Or you could talk about novelty or long-term buys, things where it's a one-time opportunity to buy something. And forecasting for a product where you're trying to estimate how much you need to buy, because you're only going to buy it once, and that's it. Unlike other ones where you know that there's going to be seasonal patterns as well as opportunities to buy it again. So these things don't necessarily always translate back to a single model, right? And that's where we think that the idea is to have a central model, and then the spokes are eventually some things that we try to integrate back into the hub. Another thing to think about here is that when we talk about business importance of different time series or different products and so on, one easy way to assess this would be something as simple as an ABC approach or a Pareto analysis, right? Often we talk about within the ABC ecosystem, we talk about 20% of your products or time series contributing to 80% of the value for your business. And then the remainder goes for like the B type ones, which is like secondary. They are around, let's say the remaining 40% actually contribute to 15%. And the last 60% of your, which is the C type of products, they're the long tail products essentially at this point. And they don't necessarily contribute a lot to the business impact from a revenue perspective, but they might actually translate to other benefits like availability and so on. Another thing that is really helpful is to think about it as it's not a stopgap solution where you just demolish the whole thing that you have in place. In industry, when you're working, you often you're already having the pain point in place, right? So having a lift and shift kind of approach, where essentially what you would do is tackle individual edge cases or individual use cases and then try to build on top of that Pareto, are often helpful. One tricky thing when it comes to time series forecasting, unlike many of the other types of ML or machine learning problems, is that it has a huge potential for data drift. And when we talk about data drift, the challenge here is that the patterns that you might have been seeing last year might not be the same that you see this year. A very easy example is to compare during COVID, for example, right? And like you might have been seeing a particular trend and suddenly there's a huge intervention that just throws everything into chaos. And now your approach, if you were using historical data to say that, oh, you know what, last year my accuracy was X%, this year it's Y%, well, it's actually not an apples to apples comparison anymore. So you want to make sure that you have some form of a shadow pipeline where you compare models in parallel so that they actually look through the same data at the same time rather than being shifted temporally in terms of assessment. And when we talk about models, it's not just the modeling approaches that differ. One of the other tricky parts of using machine learning is to understand what right metrics to actually use or assess your model with or your impact with. And different use cases often might require you to look at different metrics. As Ségolène pointed out, we talk about using distributions-based forecasting nowadays, right? Most of the discriminative models tend to end up having probabilistic distributions that you could actually select a point of. And the reason for that is to actually allow us to minimize risk. I think Jim earlier mentioned on this as well, that at the end of the day, every business is required to take some risk. And one typical method that we use here and what we recommend often when we work on forecasting problems is to look at bias on the forecast, the point that you're selecting, the value of the forecast that you're selecting, compare it to assess whether or not you tend to be under-biased, over-biased, and how well calibrated your forecast really is, especially when you look at distributions. And we talk about risk and risk in financial planning, for example. If you often tend to have an over forecast versus an under forecast, you could end up having to either do undercutting or end up having depleted cash reserves. Similarly, across other industries as well, right? When we talk about inventory planning, you've got excess inventory or you've got lost sales. And the risk here is different for different use cases, for different products, at different times of the year as well. For example, during peak season, losing the sale might be easier rather than having excess inventory and so forth. And so when we talk about these different metrics, it's not always that we recommend using quantile loss. For example, different use cases, say for example, you're working with a seasonal data or seasonal or time series data point. Working with that, knowing the fact that your data is actually skewed and has huge spikes throughout, it might not make sense to always look at percent errors. Or if you have really slow products or slow time series where the amplitude is somewhere between 0 and 2 or 3, asking for a percent error is probably going to overstate and you lose your stakeholders' trust very easily. That's where we often recommend that you need to identify which metric to use and also tackle different use cases in different ways. And so yeah, the other piece that I wanted to cover was what happens once you actually generated the forecast. And typically, and I know we had a couple of talks earlier today talking about this as well, where interpretability, when you talk about today's world where everyone's trying to use black box models all the time, well, there's still possibility to get interpretability out of it. And a simple example, in Jim's talk, he mentioned of how with the VIX or variability index, he was seeing how it was actually fluctuating. And we were talking about how that the value of that was spiking a lot during the financial meltdown or during the COVID pandemic. And these kinds of insights into the data can only be brought down by looking at interpretability from the models and looking at gathering the strengths and weaknesses of your models that you're actually using. And it's important to get this so that your stakeholders or your end users of the forecast actually understand this as well. Another example is doing what-if analyses. We often are now in situations where, given the compute resources that we have at our disposal, you can assess things or get an estimate of things before you actually end up taking a particular action. And this is super important in today's supply chain world as well as financial world, where decisions that you end up taking for a particular product, time series, or stock, or anything in general, or your option for that matter, can actually end up having lots of downstream impacts. And that's where having some form of a tool where that you can actually use this to assess, okay, what happens if my price jacks up by 5%? What happens if my price reduces by 5%? And getting a sense of your confidence around that particular period in terms of what is your tolerance level will allow you to actually create alarms and triggers accordingly. And another application here, right, is actually having experts in the loop. This is super important because at the end of the day, the subject matter expert, in this case, someone who's actually doing the deal, or someone who's actually making the trade, or someone who's actually creating some form of gathering some form of insights and feeding it back into the system, they would be allowed to actually override the forecast based on their judgment. And this is super helpful, especially during macroeconomic events like COVID, where essentially what happens is like they come in, and rather than having automated systems all the time where things just go on and create chaos downstream, you would allow them to override this in time so that the impact is minimized. So yeah, I think that's pretty much some of the insights that we've seen, different ways we've been using forecast. We believe that actually integrating cloud systems here is actually super helpful because you're no longer stuck to a given on-prem solution where it's just as is. You can actually intervene during different phases of that particular process overall. And that's where I would like to conclude. And yeah, thank you.
Thank you. And I have to apologize to you, Yash. I'm sorry, I didn't introduce you, I only introduced Ségolène.
That's
So
fine.
I'm sorry about this. Is there any question in the audience? Oh.
Let me start by just understanding the framework. You're typically trying to forecast the sales of a product or revenues, the unit sales or something of the sort. Is that right?
Sorry. So we would typically forecast at Amazon. It depends on the use case. So revenue forecasting is definitely something that you would do for specific businesses. But you would also have, say, for example, user subscriptions, right? You're trying to predict if you're trying to release a new product or a new movie, how many users are actually going to watch it as well. So that's where we would start, understanding what is it that we're trying to estimate before we do or take a particular action, right? So yeah.
And this is a service you provide your customers.
So this presentation is actually a mix of both. So the piece of historical, like how we've been doing forecasting at Amazon is thanks to both Ségolène and I. We've actually been part of the .com side where we've been part of the supply chain work. So we've done some forecasting there for products that are sold at Amazon, but it's also, the insights are actually influenced by the interactions that we have with customers. So for example, working with customers like Foxconn, or I think there's a slide out there with like lots of different customers that we've interacted with. And the use cases differ. Sometimes it's revenue, sometimes it's product, sometimes it's users and so on. So yeah.
So there's one model in which you had a hub and spoke model system. What exactly are you doing? Do you say, look, we've got a central model plus a bunch of auxiliary models, then we combine their outputs to get a better forecast?
Right. So we typically call this as an approach, it's an example of ensembling. So instead of using a single model, say, for example, you've got linear regression. You start with linear regression and you're saying that, okay, your accuracy gets somewhere around, let's just throw a number right now, you're 80% accurate.
Okay.
But the 20% that you're not accurate on, you still have an opportunity to improve that on that 20%, because you could, instead of using linear, you could probably use polynomial and you could get a little bit more, right? So the idea is to not overfit on all the individual products or time series that you're working with, but identify where which model might perform the best. Sometimes it's also a case of having certain types of data points for specific data time series that you might not. Say, for example, you're working with stock predictions, but for stocks that have been on the market, say, for example, Alphabet, Amazon, Google, Meta, or something like that, you have a lot of social data, like social, what do you call it? Let's say Twitter data, or some form of like NLP, or like some form of feedback from the social media that you could collect. But if there's a new company that's just spun off and they're going in IPO, well, historically, you did not have anything. So now you're trying to see whether there's similar similar IPOs that have happened and how they've progressed. So now you're trying to say that, okay, this one, you can't use the same approach that you're using for Amazon and Alphabet and Meta. You might be looking at a different one now because you have different kind of data here, right? So the idea behind the spokes are that they tackle niche cases where your central model might not be equipped right now to handle them.
There's actually very rich literature, both in econometrics and in information theory, about what's known as the forecast combination puzzle. You take a bunch of models, you combine them, and you actually reduce mean square forecast errors quite substantially. Even the simplest case, average, just a simple equally weighted average works remarkably well in practice, and it's hard to beat. It's a good baseline. Does that translate to a hub and spoke model, or am I thinking about it wrong?
It does in some cases and doesn't in some, right? So for example, the idea behind the hub and spoke is not necessarily always about specific niche use cases, but it also allows you to permit different ways of assessment. For example, say I'm actually going to make a buying decision for after 6 months for the remainder of the 6 months versus I'm making a buying decision right now for the next 12 months. So, well, the assessment would be totally different for both of them because my accuracy right now is the latest bit of information that I have, and that's the one that I'll be getting assessed on, versus the one where I have 6 months of time or build up to the point where I will be making the decision. So I might have a little bit more leeway in adjusting that forecast versus this one, right? So the idea behind the hub and spoke is maybe different use cases, but maybe also different assessments. So that's where we get a little bit of wriggle room in getting that. The eventual idea is that maybe you come up with a universal model that can do all kinds of sets and combinations, but it's not always possible because you won't always have all the data points on all the things at the same time. And business is often like, everyone's at a different maturity level when it comes to how much data they have. We've sometimes interacted with customers who would come to us and tell, oh, I have 6 months worth of data forecast. I'm like, okay, yeah, we want to do that. We want to help you there, but we need to know what's the seasonality on your data set as well, right? So that's where I think having stakeholders understand different nuances when it comes to time series forecasting and how to use them are very essential when it comes to something like this. So yeah.
Okay, thank you.
So thank you. We are going to move on to our next speaker.